The size of things? It's all about perspective. That's what we believe in. At Merck, we don't evaluate things by size, but by their impact on lives every day. By daring to dream big, we turn the micro into the extraordinary. At Merck, there's nothing small in what we do. What the human eye can barely glimpse through a microscope can transform millions of lives. What size is this needle? Big enough to help bring millions of babies to this world. We help create this atomic-sized marvel, paving the way for AI that could reshape mankind's future. Together, we can shape the future by taking bold steps that create lasting impact for generations. Merck, sparking discovery, elevating humanity. The size of things? It's all about perspective. That's what we believe in. At Merck, we don't evaluate things by size, but by their impact on lives every day. By daring to dream big, we turn the micro into the extraordinary. At Merck, there's nothing small in what we do. What the human eye can barely glimpse through a microscope can transform millions of lives. What size is this needle? Big enough to help bring millions of babies to this world. We help create this atomic-sized marvel, paving the way for AI that could reshape mankind's future. Together, we can shape the future by taking bold steps that create lasting impact for generations. Merck, sparking discovery, elevating humanity.
Hello, hello. Good morning, good evening, good afternoon to everyone, and welcome to PDA's webinar So, hello everyone. Thank you very much for joining us today. This is a sponsored webinar by Merck. So, just wanted to welcome everyone. We can see that there's actually quite a lot of interest already coming on board. Again, I just wanted to thank everyone, but mostly I wanted to thank Merck being the sponsor for this, and without the sponsor of Merck, this would not be possible. And the main thing is that just wanted to inform everyone that this particular topic, virus filtration in continuous processing, low flux impact on virus retention and mitigation, is extremely important. So our speaker, Karen, will be coming along very shortly. Just wanted to introduce everyone to Karen as well. So let me do a very quick introduction. Karen is the head of downstream. Downstream MSAT based in Singapore at Merck Private Limited. Yeah. She has got 13 years of experience in biopharmaceutical industry and 2 years in R&D. She provides technical support for process development, troubleshooting, and technical training in the downstream processes in Singapore. All right. She's actively involved in several process development, troubleshooting, and collaboration studies with biotech companies in Southeast Asia and Taiwan region. All right. Karen focuses on tangible flow filtration, TFF, and virus downstream technology, and had participated in several publications around single press TFF, media filtration, quality by design, and so on. Karen is a chemical engineering and graduated from the National University of Singapore. All right. I do not want to take too much of the time, so I think the floor is yours, Karen, to go through all the information that you want to share with everyone over here. There you go, Karen. Thank you.
Thank you. Thank you, Tony, for the introduction and also the opportunity to present today. And in the next 30 minutes, I'll be sharing a topic on implementation of process filtration within continuous processing, right? And also some of the challenges associated in that particular operation at low flux, in the impact on retention. And then we'll discuss a couple of approaches to optimize the filtration process in a continuous manner. And then at the end, we will summarize. Okay. So first, before I start the topic, just a little background on continuous processing. Continuous processing and the advantage of continuous processing is not new by many people now. There has been a number of publications out there focusing on the advantage. So there are a number of advantage over continuous operation as compared to the traditional batch approach. Right? For example, you get high increase in productivity by reducing the processing time, real-time process monitoring. Right? It allows you to have a better control where you can have process control in the continuous monitoring and adjustment of process parameters. This can result in consistent product quality and also reduce the variability. Continuous process also offer a reduced footprint that eliminate the needs of large batch tank or any storage vessel, for example, right? And that will also lead to a lower cost and increase in flexibility, allow for easy process modification, and can also lead to faster product development and as well as process optimization. Right. So in terms of implementing virus filtration into continuous processing, the operating condition in a continuous process are not exactly the same as they are in batch process. So, and that is something that we need to take note of. So compared to batch process operation where the batch is filtered over a few hours, the filtration in a continuous operation could occur over a period of days or even over a few weeks, right? So in this plot here, it shows flux in terms of LMH, liters per meter square per hour, as a function of change of frequency of the filters, and that is in the time which the filter has reached to at the end of its life cycle, and it needs to be changed out for batch processing with it. Right, with the batch is filtered in a matter of few hours to 2 to 4 or even up to 6 hours. The flux is generally in a few hundreds LMH range, liters per meter square per hour range. And in this, typically the operation where you have a batch, it does depend on your filter's capacity, right? So if you have a higher capacity, you can run it faster or have a longer changeout time. But generally in batch operation, we are in sort of 100 to 200 LMH range. However, for continuous operation, the processing time is spread out at the same capacity over a much longer period of time. So when we spread that out, that capacity over a longer period of time, we are going to run at a slower flow rate. So it can be 1 to 2 order of magnitude slower in continuous processing compared to batch operation. So instead of running in a couple of hours, right, in 100 LMH range, we may be running to likely below 50 LMH or even as low as 5 LMH. Right. So if we look at the LRV of MBM as a function of flux and compare that to our target value of about 4, right? In a typical batch operation, when we are running in the hundreds LMH range or even higher, right? Typically, you see the LRV is quite high. Right? The typical value that we obtain can be around 6 or even higher, well above the minimum target value of 4. Right? However, in continuous processes, as we discussed, because we are stretching out the time period over where you can capture those viruses, you are running in a much lower flux and potentially, as I said, perhaps going down to even 50 LMH or below. So, which you know, this is a couple of orders of magnitudes lower than the batch operation. So in this case, what we see that retention performance can be compromised. Right? If you go low enough, potentially even lower than your target value. Right? So this is not the place where we want to operate in a regular manner. So why is this happening? There has been quite a bit of literature on this topic, but I'm just going to give you kind of a simplified description of why is this happening. Right? At low flux, you are likely to get a complete capture that you are at high flux. Right? So at high flux, convection force are dominant. So this blue circle here represents a virus. This represents a pores through the membranes. Right? The pores through the filters are not cylindrical. They are in fact tortuous, right? Interconnected pathway, right? Which the virus must pass through. Right? And if you have a fluid of flow, the virus particle is going to follow the stream that the fluid will follow the stream of that fluid until it overcomes a certain capture point, right? And then it will essentially be stuck at that point, permanently remain at that place. However, at low flux, for the same stream, the diffusive force can be quite significant. And in fact, it will dominate the flow behavior, right? So the particle does not necessarily follow the exact streamline of the fluid flow, as you can see from here, right? And that will potentially be able to give that virus breakthrough. Okay. So this is more on a mathematical explanation of what is happening here in the pellet pellet number. The pellet number, which is a dimensionless number, is a ratio of convective transport over diffusive transport, right? So when you have a high pellet number, this is the pellet number as a function of flux for a virus filter's membrane, right? At a very high pellet number, the convection force is dominant, as I explained earlier on. And again, the virus particle will follow the streamline, and once it's encountered a choke point, it will get captured and permanently stay there, right? At low pellet number, the diffusion become more dominant, and again, the particle has an opportunity to diffuse and give enough time, enough opportunity, potentially find an escape pathway. Right. As we said, the batch process, we are operating in the 100 LMH range, right? Typically in a range where the pellet numbers are well above the one order, is matching above one convention, which is dominant. We see that the particle follow the streamline convective transport is dominant. It does not have the opportunity to maneuver around, right? Eventually or potentially find an escape pathway. However, in a full continuous process, when you are running in low flux, as low as 10 LMH, right, perhaps even lower, your pellet number will approach to 1 or even go below 1. Right? So, and again, that's where there's an opportunity for the virus particle to potentially find a pathway and escape through to the downstream side. Right. So this has been recognized in a number of publications that discuss virus filtration within continuous processes. This publication know that low flux operation may impose a limitation on how the virus are used. And so a conventional approach to overcome this limitation is essentially also needed to operate the virus filter as a batch process within a continuous process. So how does that look like? Right? It will essentially look like you will have a surge tank on the upstream side, right? And on the downstream side of the filter as well. Right? And you operate the filters perhaps in a few hours a day, and you change it out each day, so it becomes a daily operation, right? And so in a certain way to implement virus filters within a continuous process, but if you do that, right, you will kind of lose some of the benefit of continuous processes, right? And having the daily change out does not really make it a full true continuous operation, right? So again, you are running in a few hours a day, and then you are stopping it for the rest of the day. So in the next session, we will talk about how we can overcome some of these challenges, and there is a couple of operational approach that we are going to discuss today. So one of that is what we call intermittent batch processes. What is intermittent batch processes? In a conventional batch filtration within a continuous processes, it uses one filters a batch, as we discussed a few minutes ago, right? You have a daily change out of the filters, So you have a filters in place, work in the first day, right? And you change it out, put the second filters, you change it out again, right? To the third filters, so on and so forth. So essentially, you have a batch operation within a continuous process. However, there is also another approach, which we call intermittent batch filtration. And in this case, instead of having multiple smaller filters, right? We have one single larger filters, and instead of changing it out every day, you only operate for a portion of its membrane capacity for each day. So essentially, you have multiple sub batches within the filters, right? So for example, you can use a quarter of its capacity on day one, right? You stop it, right? And then use another quarter of its capacity on day two and stop it, right? Without changing it out, right? And use another quarter, so on and so forth, until you utilize the full capacity of the filters, right? And in this case here, it is in this case, in this way, you will significantly reduce the number of filter changeout. It is not completely continuous, but it certainly get you closer to the continuous operation, right? It minimizes the number of filter changeout that you have to do. So we also want to evaluate this approach, and we did a study on this. And so in this study, we use a map at 6 gram per liters concentration, where we target about 900 liters per meter square, run it over 4 days, and we spike it at about 6 lot of MVM. It's run for 4 hours a day, 60 LMH, right? There is also a 15 minutes interruption introduced into the process. And then at the end of each day, we had a buffer recovery at 100 LMH for 10 liters per meter square. So as you can see here, it used a single set of device. And over at the bottom right corner, this is a plot of throughput versus time. Day one for 4 hours, about 240 liters per meter square throughput. And we had the buffer flush, right? And it stopped for 20 hours, and then restart for another about 240 liters per meter square, followed by a buffer flush, and so on, until it reached the end of the 4 days. So in one field, one filter that's operated for 4 days without any change out. So first, I'm going to show the result in terms of the plugin profile, right? And in this graph here, you see pressure versus throughput as the membrane file. The resistance increases. So at this constant flux operation, the following translates to a pressure increase, right? And what you can see here in the plot of pressure versus throughput, we have small amount of fouling after day one. And that's really important, is that what you see at the start of the second day, right? It essentially pick up right where it was left off. This spike in pressure that you are seeing in the graph is from the buffer flush, right? And from the shutdown, right? And then it going from day 2 to day 3, again, it pick up right where it was left off, right? And so on until it reached the destination filtration endpoint. So you can see from those 4 replicates here, and each of them being very similar to the others, and we achieved the profile as what we expected as well. So running in discontinuously is not a lot of different wave if we run it continuously for the entire period of time in terms of the actual throughput performance. Right. And of course, the LRV performance is very important, right? And what we show here is the MVM retention. right? What we found is that either at low or no detection across all device and all filtrates and also buffer flush. LRV are all well above 4. They are above about 6 in all cases. We sample the filtrates from each of the 4, right, on day 1, day 2, day 3, and also day 4, and so forth. The buffer flush, and what you can see here is that all the runs are well above the target of 4 LRV, up to 6 even. So we considered this a successful demonstration that you can run batch intermittently with a single device, allow you to minimize the amount of filter changeout. Okay. So to summarize, the intermittent batch filtration process, a key advantage is to reduce the filter changeout frequency, right? You need somewhat smaller surge tank size because you are running it intermittently and actually allow for low impact on the upstream processes, right? Upstream properties exclusion, and as well as most importantly, avoid a low flux condition where it can risk in reduce virus retention. So if we will go to our second approach for optimization performance in continuous processes on serial filtration at high area ratio. Right, serial filtration is not a new idea. It is not a new concept, right? There has been actually a few publications which we listed down here, right? And these papers talks about serial filtration, right? So why do people do that, right? The primary benefit of having serial filtration is to have a greater retention, virus retention. Virus assurance across both stages as well, right? If you have 2 virus filters connected in series, any virus that manage to pass through the first filters will very likely be captured in the second filters, right? However, then the disadvantage to this approach will be on the cost, right? If you double the number of filters, you will have just doubled the number of costs as well. So if you are in a 1-to-1 or 2-to-1 ratio, in as what shared in some of these articles, right? You will be at 1 to 2 times higher in terms of cost, right? So yes, you may have a much higher LRV retention, but a significant cost impact will need to be in consideration as well. So the question is, do we really need to run serial filtration in 1-to-1 or 2-to-1 ratio, right? Maybe the answer is we don't need to, right? We don't necessarily have to run it in 1-to-1 or 2-to-1 ratio, right? So as you can see here in the bottom right corner, right, it's a relatively larger device. This is a VirusSoft Models 1.3 device that contains 0.22 meters square of membrane area. And if we run it in a very low flux into these filters, you will run in a very low flux of about 5 LMH, right? So it can potentially have a very relatively low LRV as well, right? However, in the second filters, which is a much smaller filters in this case, is actually 13 times smaller in membrane area, right? It's going to have 13 times higher in flux. So this has a couple of different benefits. All right, first of all, it will sort of do a worst case scenario where we actually drop below 4 in the first stage, let's say 3, right? And the second stage, it operates at a relative high flux and we do not have impact on the retention, right? You will probably get a maximum of LRV, which is, let's say, about 6, right? So now these LRV are additive, right? And or at least at the theoretically, right? You have an LRV of 9 in total. Much higher LRV, and you will not have to double your filtration area required. And you only have to add them, right? So like in this case here is about 7% more area. So by adding a little bit more of filter area, you get a huge increase in retention assurance. Right. Yeah. So we want to do an experimental evaluation of this approach, and we ran a study. In this case, we actually use a modus 1.3, right? And again, this has a 0.22 meter square of membrane area. We put that upstream of a modus 1.1, which contains 13 times lesser in membrane area. And we run the first stage at about 5 LMH, which means the second stage of the device will be running at 65 LMH. Right? We run it for about 200 hours at about 1 liters per hour. Right? And we challenge it with a feed stream that was intentionally loaded with a lot of aggregates. This is meant to demonstrate a worst case scenario. Right? Also, we did not have any pre-filtration intentionally in this case, and that's because also we wanted to sort of do of a worst case scenario. Right? We spiked it with MBM at about 11 lot at 3 different time points throughout the 200 hours, which I will show you some more details in terms of timeline later on. Right? We had also process interruption planned within the process, and very importantly, we collect data not only across the filtration train but also at interstage. Right? We measure the pressure in between the stage. So essentially, we could do a direct comparison in one experiment of what would happen if you just have single stage versus if you have 2 stage in series. And again, that's allow for a direct comparison between the 2 approach in one experiment. So a little bit more details in the timeline. Again, this was run for 200 hours. It was spiked with 11 lots initially, and later on we spiked another 11 lot and another 11 lot. So total 3 times of 10 to 11 lots. We had some planned process interruption, and to look at the effect of that. We also collect all the filtrate, and we did it in 24 hours pool, and then sample from each of these pool. So we knew that at the end of each day what the total virus breakthrough was. If there's any in addition, we created more pool in intermittent after a spike and immediately after a process interruption, which get a final solution on the impact of those events on virus retention. So I'll get right to the result. First, in terms of capacity, we can see that this is the pressure drop across each filters in the total and across the filtration train, right, as a function of operating time. Right? At first, the first stage filters operating at 5 LMH has very, very low pressure drop in the profile. Right? The pressure drop at 5 LMH is a fraction of the total PSI. Right? The second stage operating at 65 LMH has 13 times higher in pressure drop, exactly what we would expect. Right? And it actually dominate the total pressure drop across the filtration train at the beginning of the run. So as the filtration progress, again, we challenge this with high plugging feed stream. The pressure increases as the membrane fall, right? And we can see that the progression of the following across the first stage of membrane and also across both stage membrane in series until we stop it at 200 hours, right? When it reached the filtration endpoint, which we designated at about 20 psi. You can see that by the end, it was the first stage that dominated the total pressure across the filtration train. The second stage experienced very little plugging, which is within the expectation also, because it was protected by the first stage of filters. And we can see that more clearly on the right side of the graph, right? If you plot it against, instead of versus time, we plot it in terms of throughput, right? And because of the second stage filters has 13 times higher in the area than the first stage, right? It has also 30 times higher in terms of throughput. So we went all the way over to about over 12,000 liters per meter square on the second stage, and again experienced very little plugging. So in principle, while the first stage filters had reached the end of its useful life, right? Over here, the second stage has not reached the end of its capacity yet. And at least in principle, this could continue to be operated beyond this point here. Okay. We will talk a little bit more about that in a minutes, but for now, it's also very important to look at what is the LRV result in this approach. Right? So over here is showing the retention performance in two stage. Right? First, I'm just going to show the total MVM in the feed stream as a function of time. Right? As I mentioned, there are 3 spike points here. And part of the reason we have multiple spike point was because it was a moderate loss of infectivity with time. So we supplement that of a couple of different points, and we measure the filtrate concentration at this stage. So we measure roughly about 7 lots in the filtrate, slightly increasing with time as filtration progress. So from then, we can see at what stage when clearance was, which is of course the lot of MVM in the feed stream minus the lot of MVM in the filtrate. And when you do that substrate, you get an LRV somewhere about 4 range, right? Lower than 4 range. And this is exactly what we will expect in the 5 LMH feed flux range. Right? But if you go down sort of a worst case scenario, you approach sort of a minimum value of 4 that we want. Of course, this kind of barely make it in this case is not what we want to be working on in that period of time, right? So we want that minimum value. So now look at what happened across the entire filtration train of 2 stage across the entire run. Right? And across every sample that we measure, there isn't a single virus detected in the second stage across the filtration train. Now there is 200 liters of fluid that was processed, and only sample a fraction of that. So that is only a sample of fraction, right? And this hour pointing down means that there are less than 4 lots in the filtrates. And this is at 95% confidence. So what we can say that at 95% confidence that across this clearance, across the both stage result in MVM greater than 6 to 7, theoretically is going to be higher and have some additional experiment planning to try to increase that assay limit, right? What we can say, at least for now, is that for 200 hours of run, there is no virus detect in any of the stage filtrate, right? At any point during the filtration, we can look at exact same data, which in terms of LRV, instead of looking exact sort of raw data of MMV, right? And again, what we see is that in first stage, the data translates to an LRV is roughly about 4 throughput for the entire run at this 5 LMH. But across the filtration train, we see LRV greater than 6 or close to 7. So that is one example that we use, and we did a study to confirm this approach. Right. So that was one example, and we did that to confirm this approach as a function of what we expect, right? But we use that data to inform a simulation, that a theoretical case where we will say, we will say, how do we optimize the size of filters using the first stage and the second stage? So we assume a continuous flow rate of 10 liters per hour. That kind of range, you will see some sort of published case study, right? And we assume a significant flow following this kind of relatively worst case scenario. And this become 90% plug after processing 1,000 liters per meter square. So the second stage will be largely protected by filling the first stage, where a much higher capacity, 50 times higher than what we assume, right? And this is actually kind of conservative, right? And we saw over 100 times in our actual data, right? So I'm going to show the result of a simulation in terms of filters productivity as a function of filter changeout again, right? That changeout time is when the filter reach the end of the useful life, right? And you will have to replace the new filters with a long time in processing. Is a very high productivity at the end of the long changeout time, so you can run it continuously for a very long time before you need to change out, right? So first for all, in order to get a full capacity, we try on a longer time, right? We put a relatively large filters, and this particular case is a Magnus 2.2, which contain 1.5 meter square of membrane area, and we run it at 150 hours at a very low flux of 7 LMH. This is kind of like a worst case as well, right? And LRV could potentially be lower than 3, right? So you get a very high productivity, but potentially, and also at potentially 90% flux decay, right? And it's certainly a reasonable change-out time, but the LRV is not reaching our target, right, of 4. So to overcome that, if we put smaller filters, in this case, we could put a Magnus 1.2, right, which for that same flow rate, a smaller filter is going to have a much higher flux, and you will get a very good LRV, well above your 4, but or in fact actually 6, because you are running at a very high flux. The capacity will exhaust relatively quickly in just a few hours. So again, in the 3 or 4 hours, you will essentially going back to batch operation. And by doing this, you will lose some of the advantage of a continuous processes, right? So somewhere in between, using a modus 1.3 is kind of in between the two scenario. Flux is 45 LMH, a little on the low side, but still okay. You know, you will not get the maximum LRV you can get, but certainly above the minimum, right? And in this case, you can run probably at about 20 hours or so, right? And certainly longer change-out time. And in fact, still a daily operation unless you use intermittent batch process, right? And you can go to a much larger value and sort of do this day after going up and change out the process. It will not be truly a continuous processes. So if we were to consider serial filtration at high area ratio, one thing simple thing that you can do to take this modus 1.3 and put it at the downstream of a Magnus 2.2. What you see here is, first of all, the LRV will achieve way higher, right? Because we are adding both filters LRV together, right? And because the second stage of the filter doesn't experience any fouling, the area ratio here is about 7. Of the first stage is operating at 7 LMH, right? Although we have 2 filters running in series, the actual delta P across the filters is actually still way below. It's only at about 12 psi at the end of the process. So we do have so much of a retention performance to spare, potentially can extend the life of this first batch instead of running it at 90% flux decay, and when we convert it to 95% flux decay, or maybe even higher, it will be on the more of the conservative side. So that concluded that by doing a serial filtration, we are really enabling a true continuous virus operation and maintain a robust retention performance here, right? So you get a higher productivity, longer change out, and a much higher LRV. If a second stage doesn't suffer any plugging, we can potentially change out less frequently than the first filters to improve the overall filters productivity. Right, so this is my last slide. In summary, in contrast to batch operation that we typically run at a high flux, virus filtration in continuous processes operate in a much lower flux, which has a risk in reduce of retention performance. Right, there are 2 approaches that we introduced today, right, that enable virus filtration in a continuous manner, in a more robust performance, and that is intermittent batch filtration, which aim to reduce the filter changeout frequency, and the other one is on serial filtration at high area ratio, which has several advantage, right? Some of those are higher productivity, longer filter changeout time, and also a much higher LRV. So I do want to acknowledge a team from our global R&D, and also leaving a QR code here for any questions that you may want us to address. So I'll pass the time over to Tony.
Hey, Karen, thank you very much indeed. Very, very informative, very, very educational deck that you've actually shared with us. I think we've actually got a few questions from the comment section. Just wanted to inform everyone that's online in the moment right now. If you want Karen to answer any of your questions or any questions that you might have, please type it in the comments section. You've got a little comment section over there, and just type it in. Julia, we see that you have got a question, but let us answer one particular question prior to you. Julia, will come to you. Yeah, I think from this gentleman or this lady, I'm not too sure. AJ, Karen, I think you're quite familiar as well. What are the critical parameters that influences virus retention in continuous filtration systems? I think that's a pretty common question that you probably come up with. Then, yeah, over to you, Karen.
Yeah, thank you for the question. I guess to call any parameters a critical parameters will require data to show that it does has an impact in the virus breakthrough for virus filtration case, or any impact in the product quality, right? From the session that we shared earlier, we can say that flux is a critical parameters, as if it went below a certain range, the LRV value decreases, right? So that can be considered as one of the critical parameters, but other parameters should also be considered as key parameters, include like throughput, pressure, applied pressure, flow rate, flux decay percent, right? Process interruption, hold time, etc. So these are some other typical process parameter that were required to demonstrate during viral clearance study typically.
Thanks, Karen. Yeah, I hope it answers your question as well. Julia will come to you at the moment right now. Karen, the question that Julia has is that how do you demonstrate virus clearance in a continuous process compared to batch process?
Right. So in a few areas we have to demonstrate, right? We have to determine what is the steady state validation, right? Ensure the process reaches or maintain consistent condition before and during the virus processes, right? And we do also need to be able to develop a small scale model, right? Because that small scale model will be required to do viral clearance. And that small scale model is supposed to be able to represent your large scale processes, or even at least demonstrate a worst case. In the continuous processes, depending on how everyone plan to run, there's a few manner we shared too just now that we do also see multiple train running in cycle, right? So those spiking, those will also link to how you plan to spike your viral in your small scale model, your spiking strategy, right? Sampling strategy as well, when and how many to collect the sample at multiple different time point, right? If this is related to low pH inactivation, we do also have to also consider about the resident time distribution and characterize them and understand how long the material is going to stay in the system, which will affect the viral clearance, so on and so forth. So these are some of the consideration when we are doing virus clearance for continuous processes.
I thought it is quite detailed though, your explanation. Julia, I hope that that answers your questions as well. Yeah. If not, please do type in the comment. Any other questions that you might have in relation to this particular question that you have. Then, Misha, we come to you. What are your thoughts on already existing low flux filters in the market? Okay, and who will they perform better in true continuous mode? Your thoughts? Which means that you probably need to do a bit of a comparison on some of the market competition then, right? No name is mentioned, but let's give us your thoughts and your thought process itself, on what the market have at the time being.
I guess there is advantage, pro and cons on different filter performance in the market, right? And it really depends on how virus filter are used and implement into the processes and running it in continuous manner, right? For example, in the high area ratio approach that we shared earlier on, it will be only possible if the virus filter give a high flux performance, right? So in those approach and those option, we see an advantage of having a virus filter that gives a typically higher flux performance than one that give a lower flux, right? But if today we are not thinking about high area ratio option, we are thinking about some other option, then perhaps low flux filters may have its advantage on its own as well. Yeah, I hope that answer.
Misha, I hope that is a very answers your questions itself. Yeah, on this, it's going to be a bit tricky, Misha, when you ask for, what are the markets that's actually, still available for all these things itself. Then I wanted to let everyone know as well. Yeah, there are some regulatory reports on this particular topic itself. Both from ourselves, PDA, we've got a technical report called TR41A that was revised back in 2022. So it should be quite updated. Yeah. Another report is ICHQ5. I think it is. Yeah. Karen, correct me if I'm wrong.
Yes,
So
correct.
yeah, thank you so much indeed. Yeah, so these two reports from the regulatory perspective, you can actually get it. Of course, ourselves, from PDA, if you're a member, you'll be able to get it free. So do take a look at it right now. I think my colleague has already type it into the comment section. PDA Technical Report 41, revised in 2022, and that's the name of the report. Yeah, and then of course another one is ICHQ5. It's ICHQ5 or ICHQ5A, Karen.
Q5A revision 2.
Okay, there you go. So both the reports are revised, so it's revision 2, and ours is revised as of 2022. Yeah. Okay. Do you have any other comments, anyone and everyone? If not, then I do have a comment myself. Karen, how do you demonstrate virus clearance in the continuous process compared to batch processes? Which I think it is almost similar to the question that was asked earlier on, right? Okay. Then maybe, coming on to that, key considerations for virus spiking studies in continuous filtration validation.
Key consideration again.
Key considerations for virus spiking studies, okay, in continuous filtration validation. What are the key considerations?
Yeah, I guess it is also very similar to the question earlier on. The spike method, the sampling methods, and spiking strategy, things like that. So I think all in all, it's all about how do we qualify and validate continuous virus filtration, right? As you also mentioned about two document, PDA Tech Report 41 and also ICHQ5A. Both of these provide some guide, and even some guide from FDA document is also available for us to use as a reference. But generally, we should have a scaled down model that simulate the real manufacturing processes during the validation. For both approach that I shared earlier on, or any approach, right? We can suggest to apply quality by design and also risk assessment to identify what are the process parameters that will affect the processes, that will affect the virus retention, right? And in the case of intermediate batch process, for example, if, for that case, the system will be put on hold, right, over a period of time, overnight, right, 20 hours, 24 hours, depends, before the next sub-batch. So there may be also concern around bioburden, right, and those concerns will also have to be included in the qualification and validation run.
Right.
On the high area ratio serial filtration, on top of what all those that I just mentioned, we must be able to demonstrate the area ratio in the small scale. This is something that we have been working with. Today, there may not have a lot of small but bigger, but not as big as a big device used in a pilot scale to run in a validation that will require a lot of sample or a lot of virus spike. So to find that area ratio to be able to run viral clearance in a smaller scale is critical as well.
Wonderful. Thanks, Karen. Karen, actually, now that you've mentioned some of the do's and don'ts and everything and all, there's actually a probing question here on my end itself, though. Um, how do you choose a specific filter for a specific virus? Virus
Um,
has specific criteria, right? As opposed to different type
mhm,
of virus
mhm,
and everything and all. So, do
mm,
you have a particular formula? What are the steps, to be taken? What are the do's and don'ts? Which I think you have actually covered it a little bit earlier
mhm,
on, right?
mhm,
What are the things that you should actually do? What are the issues that you might probably want to be open about it and all? But maybe down to the specifics, I don't know, is it a little bit too difficult for you to answer? Difficult in terms of not trying to be a little bit more skewed towards, Merck side, but just trying to be a little bit more balanced. So,
mhm, mhm.
how do you choose a specific filter? Not naming, any particular brand.
Mhm. Mhm.
Just trying to be neutral. That's
No,
why.
no worries. Yeah.
Yeah.
So, in a typical process development
Mm.
process, and if we are looking at choosing a virus filters, at that point of time, that virus spike is not has not started yet. So the
Mm.
at that point of time, we are looking at the virus filter that give the highest throughput within the target success criteria, such as processing time, and as well as yield, things like that. So both those criteria will need to be decided at the beginning to select the right filters that meet your success criteria. And at that point of time, it's looking more like the throughput comparison, and mainly because virus filters are not the cheapest, right? And therefore, we should have one that give you the smallest membrane area to process the requirement, right? Once that is done, this is just only on the economical perspective and also yield perspective. It will then move on to a virus spike. Choosing what virus, it depends on the cell line, in fact, right? For a MAP process, there is a very established virus model panel to be tested, right? MLV, right? MMV, real, and PRV. These are the four model virus. And why these four is represent different type of virus, right? Single-stranded DNA, double-stranded DNA, different sizes, right? And if it's tested out this four model, it more or less cover majority of the um, potential risks, right? But if today this is not a map, if today this is a cell gene therapy, right? There is also a guideline on what are the virus panel to support which virus to be tested.
Yeah, very interesting. So really, it's all dependent on the type of viruses that you're talking about, and then what kind of filters is actually probable enough, to do the filtration for that itself. Then I suppose this also comes on to the next question itself. Do we have time? We are a little bit off though right now. So I suppose I'll just throw in one last question, Karen. Yeah. Is there any alternative to maximize the yield of filtration if in the current process has higher percentage of retention than the previous studies without changing the filter membrane?
Mm, mm. Um, yeah, generally to speed up the filtration time without changing the filters,
Mm,
one can increase the membrane area, right? Uh,
that's a
but
fair
this
comment.
also means that it will be higher cost, right? Running at higher
Yeah,
flux
yeah.
can also help to reduce the filtration time, right? Meaning you run it at a higher pressure
Mm.
and push the fluid through in a very short time. But this will change the parameters and whether or not you done your validation, are you allowed to do that? If not, it will require you to do a revalidation, right? And if your
And that
previous
takes
data
time.
it's not sufficient, you have to re-demonstrate that. So with regards to how to maximize yield, and if there's any experience in change in yield recovery observed from batch to batch, the suggestion here will be relook into your recovery strategy, right, such as buffer chase. Recovery method is also part of the key process parameter, right, just so you know. Right, so when considering changing the recovery method, such as your buffer chase, loading, things like that, would that actually affect your virus retention performance? This also needs to be in the consideration.
Yeah. So it is a pretty tricky question itself. Basically, you got to wait amongst, what you have between time and between costs, right? Yeah, so you're also dependent on the facilities that you have as well. Okay, I think that's about wrap up everything already. I hope all questions are answered and everyone is actually satisfied. With the presentation, with the answers, and with the quality as well, and all. Thank you again to Karen, giving us a wonderful presentation, an extremely educational presentation again. So like I've mentioned, in relation to Karen's presentation and the topic itself as well, there are two regulatory reports. One, ourselves, PDA, has got our own technical report, number 41, which is revised back in 2022. And the other one is ICHQ 5A. So both are available. So if you're a member of PDA, you can actually get it free and download it and all. ICHQ, you need to go to ICH to get the member report itself then. So I suppose we will wrap this up. Again, thank you so much indeed, Karen, for your wonderful presentation. And thank you, Merck, for sponsoring this particular event. Yeah. I wanted to just spend a little bit one more round to let everyone know that we've got our upcoming conferences, which is a couple of weeks' time in Korea, and it is called Aseptic Processing of Biopharmaceutical Conference. All right, it runs for 2 days, 4th to the 5th of November. And then after that, we've got our Japan conference. Oh, we've got in Korea, which is the post-conference workshop, strengthening CCS, contamination control strategy in aseptic manufacturing workshop 2025. Then, yeah. I would like to also inform you guys that we've got the CGT Pharmaceutical Product Conference as well. Okay, without further ado, this is our calendar for 2026. We are all full. We are all planned out for 2026. Do mark your calendar. So we've got the conference in Singapore. We've got a conference in Thailand. We've got a conference in Taipei, Taiwan. We've got a conference in Australia. And we've got a conference in Korea and Japan. We've got a full calendar next year, so we're talking about roughly around 10 conferences and workshops all together in 26. So mark your calendar. Do give us, any questions that you might have. Send us, any information through email or whatsoever. We'll be very happy to assist you on particular topics, CGT all the way to aseptic processing, to biopharmaceutical, to contamination control, to microbiology, and all that. Yeah. So thank you so much indeed, everyone, for calling in, and it has been a wonderful evening. Have a good one. Bye-bye.
size of things, it's all about perspective. That's what we believe in. At Merck, we don't evaluate things by size, but by their impact on lives every day. By daring to dream big, we turn the micro into the extraordinary. At Merck, there's nothing small in what we do. What the human eye can barely glimpse through a microscope can transform millions of lives. What size is this needle? Big enough to help bring millions of babies to this world. We help create this atomic-sized marvel, paving the way for AI that could reshape mankind's future. Together, we can shape the future by taking bold steps that create lasting impact for generations. Merck, sparking discovery, elevating humanity.